Welcome to DP Tutorials by Donny Jirwa. In this teaching module, we will learn on one topic, which is to find the electric field due to a uniformly charged charged plane sheet. Over here we have this charged plane sheet, in which on one side we have the charge accumulation, which is positive, and on the other side we have the charge accumulation, which is also positive. So we have learned that for positive charges, the electric field lines will be directed radially outward. So I have these yellow vectors. Let these yellow vectors represent the direction of our electric field. Okay? Let these yellow vectors represent the direction of our electric field. So due to one side of the sheet, this electric field will be directed on this direction, and due to this side of the sheet, the electric field will be directed on this direction. So from here we know that if Q be the charge, okay, if Q be the charge and A be the area of the shield, then the charge density of the shield will be given by Q divided by A. Okay. Charge per unit area, charge per unit area is defined as our surface charge density. Okay? Surface charge density. So that is Q divided by A, which means that Q will be equal to sigma times A. Q will be equal to sigma times A. Then, let us consider, for instance, suppose there are 2 points Q and there are 2 points P, which is at a certain distance, okay, which is at a certain distance, say like for instance R from the shield, and also like a distance R from the shield. So how will you find the electric field at these 2 points, which is equidistant from each other at a distance R apart from the shield? We have to construct a Gaussian surface. We have to construct a Gaussian surface, and that Gaussian surface constructed should be in the form of a cylinder. So from here I have considered 2 points which are equidistant at a point R away from the shield. So in order to find the electric field through these points, what do you have to do? You have to construct a Gaussian surface, but a Gaussian surface in this case will be of the shape of a cylinder. And then due to this Gaussian surface, then you will be able to find what? Then you will be able to find the electric flux. So now let us first consider a Gaussian surface. Okay. So now from here, let us consider a Gaussian surface. We will remove some of the terms. Okay. We will consider a Gaussian surface, and with the help of this Gaussian surface we will try to find the electric field at these 2 points, okay, P and Q. Okay, at these 2 points P and Q. Okay. So we will take these Gaussian surface, and then I will put such that we will take this Gaussian surface in such a way that it passes through or it bisects this cylindrical surface. Okay? It bisects this cylindrical surface. So that is our Gaussian surface, which is in the form of a cylinder, and over here we will take these 2 points. Okay? This is point P at one end of the cylinder, and there is another point Q at the other end of the cylinder, and these 2 points are a distance R apart. Okay? These 2 points are a distance R apart from one another. Okay? They are a distance R apart from one another. Okay? Similarly over here, the distance of this point P is also R apart from the center of the shield. So from here, it is very clear that we have to represent the the direction of the electric flux or the electric field due to the end caps. These are called the end caps. Okay? Due to the end caps and due to what? Due to this lateral surface. Okay? Due to this lateral surface, you have to find this part. Okay? This part is what is known as the lateral surface. You have to find what will be the flux according to that area. Okay, what will be the flux across that area. Also, you have to find the electric field due to these end caps. Okay, you have to find the electric field due to these end caps. So we have to consider certain sets of vectors. That means the electric field vector and these are our end caps. Okay? This direction from here is also our end cap. Okay? So this is the right end cap, and this from here, this will be our left end cap. Okay? So this is our end cap. This is the left side of the end cap, and this will be the right side of the end cap. So from here, you have to consider, that means since the electric field lines are directed away, since the electric field lines are also directed away, we will take these sets of vectors. Okay, we will take these sets of vectors. Let this yellow colored vector represents the electric field vector, and also this yellow colored vector represents what? The electric field in the electric field of that Gaussian surface. So from here, this will be our electric field vector, and also this will be our electric field vector. Okay? So that is our electric field vector. Then from here, if I consider a small element, which is our ds bar, okay, if I consider a small element through that end cap, which is ds, then you have to represent the area element. So let this green vector represent that area element. So that green vector will represent what? That green vector will represent our ds bar element. So from this case, the angle between E and ds bar, it is how much? It is equal to 0 degrees, since they are acting on the same direction. Similarly, on this end of the surface, if I consider that small element, which is our area element, then I have to draw also the area element vector. Then I have to represent that by another vector. So let me take this vector, and this will represent our area element vector, and at this point P, okay, in the representing in that direction. So this will be what? This will be our ds bar element. In this case also, both E and ds are in the same direction, so it is evident that the angle between them is how much? The angle between them is 0 degree. Then we have determined the electric field due to the end caps. We have determined the electric flux, I mean, due to the end caps. Electric flux is E dot ds and E dot ds. So then next we have to find the electric field due to the lateral surface. So from here, the electric field due to lateral surface, that means you have to consider the area element in the upward direction. That means if I say lateral surface, that means if I consider one element over here, ds, that means this will be one. This will be our area element. If I consider corresponding element from this side, that means on the lower side, the area element vector will be on this direction. So those are the certain features. Okay? So now we will take the sum of the vectors. So from here, let me take this as our area element along the lateral surface, and then we will represent the area element vector due to that uh, due to that element. So I will take this green vector. I will take this green vector, and this green vector will represent our area element vector. Okay, area element vector. So we'll take this and I'll put it here. This is our area, corresponding area element vector along the lateral surface. Then if we have this sheet, and if we consider only one side, that means this is the side which is opposite. If I consider only on one side, this is the one side of the sheet, what will happen? The electric field will be 1. The electric field will always be in this direction. So with respect to this direction along the lateral surface, the electric field will be in this direction. Okay, the electric field, that yellow vector, will be in that direction. So that is the direction of our electric field. So which physically mean that this angle between E and DS, this angle over here, that theta will be equal to how much? That theta will be equal to 90 degree along the lateral surface. Similarly, we will take these sets of vectors, and also we will take these sets of vectors to consider another portion of our Gaussian surface or lateral surface. Say, like for instance, if I take from here, it will be the same like this. If I consider another surface from here, that means let that area element be ds, then the area element vector will be represented by this vector. So that is our one. That is our ds bar area element. So this electric field is in this direction, so we will represent this vector, and this vector should point on that direction. This vector, which is our electric field vector, this should point on that direction. Okay. So this is our electric field vector. This is our electric field vector, and this electric field vector along the lateral surface is pointing on that direction, which means this will be, for this element, electric field is on that direction. Okay? The electric field element is on that direction. So from here, it is evident that this angle also between E and ds is how much? That angle over there, it is how much? That angle is 90 degree. Okay? That angle also is 90 degree. So if you want to find the flux due to this Gaussian cylindrical surface, number one, the flux that you have to find due to this Gaussian cylindrical, due to that Gaussian cylindrical surface, is that you have to find due to the end caps, what will be the flux due to the end caps. And number two, you have to find the flux across what? Across the lateral surface. So determining the flux, you can find what? You can find your electric field. So determining the flux phi, you can find the electric field. Determining the flux, you can find the electric field, because this is the concept about what? About electric flux. And according to Gauss law, this electric flux will be equal to what? According to Gauss law, the electric flux will be equal to Q divided by epsilon. So from here we have done the construction of that part. Then from here, from Gauss law, the electric flux due to the Gaussian surface, okay, due to the Gaussian surface, will be given by this expression, and this is the concept of our electric flux. Then this should be equal to 1. This should be equal to Q divided by epsilon naught. But this electric flux, okay, this electric flux of this Gaussian surface is due to 3 parts. That means there will be 3 contributions: the left cap, the right cap, and the lateral surface. So from here, let us mark some of the equations as equation number 1. Let this be equation 1, and let this be equation 2. So from this equation 1, okay, from this equation 1, we have determined that along the lateral surface, okay, along the lateral surface, what is the angle along the lateral surface? So along the lateral surface, this is the lateral surface. Okay, this is the lateral surface. So along the lateral surface, how much is the angle? The angle is 90 degree. Along the lateral surface, the angle between E and DS is 90 degree. And along the end caps, the angle is how much? The angle is 0 degree. Okay? Along the end caps, the angle is how much? The angle is 0 degree. Along the end caps, the angle is 0 degree. So along the lateral surface, that means the angle between the electric field vector and the area element vector is 90 degree, okay, along the lateral surface. So from here we will try to study, okay, we have to study what are the contribution of the integrals due to the left cam, the right cam, and the lateral surface. So we have split the angle between the lateral surface. For the lateral surface E and DS, angle is how much? Angle is 90 degree. And from here we can ensure that if we take the dot product, if you take the dot product, that is the concept, then this will be a E ds, and then you have to put cos of 90 degree. So cos of 90 degree will be equal to this, cos of 90 degree is equal to 0. So this integral itself will be equal to 0. So there will be no contribution. Okay? There will be no contribution from the lateral surface, which means that this integral will be equal to 1, will be equal to 0. So the contributions will be only from the end caps, whereby if you look from this figure also, the through the end caps, okay, through this right end cap and from this left end cap, the electric field passes, the electric field crosses, the electric field passes through this end cap. So there will be electric flux. Okay? There will be electric flux. So from here, the angle between E and DS, the angle between E and DS is how much? The angle between E and DS is 0 degree. So from here, calculating the electric flux, that means this will be E dot ds bar, and from here this will be integration of E ds, then it will be cos of 0 degree, but cos of 0 degree is equal to 1, so which means that over here you have only the integration of E and ds, okay? E and ds from both the end caps. When I write end caps, that means from both left and right. So from here we will calculate what will be the total flux. What will be the total flux from that equation 2? From that equation 2, we have that the electric flux due to the lateral surface will be equal to 0, and from here that integration, okay, that integration from here we have we can write simply integration of EDS. Okay, we can simply write integration of EDS plus integration of EDS. But through that entire surface, E will be equal to 1. E is constant. Okay? E is constant. So E is constant. E is constant. And if E is constant, that means you can take that outside. This is 0. So E is constant, we can take outside of the integral. We are left with integration of ds. Even from the second integral, E is constant, so we can take outside. Okay? But this closed integration of ds, it is equal to what? It is equal to the area of the end caps. Okay? The area of the end cap. See, if you look from that end cap, if you look from this Gaussian surface, this area over here, okay, twice r. If you take only this is r and this is r, from this point up to this point, it is equal to small r. From this point up to this point is also equal to small r. That is why the radius, okay, the length of the cylinder, is 1. The length of the cylinder is twice r, and the area is 1. The area is a. So from here, which means that this area over here, that area over there, okay, this will be 1. This will be equal to A. That area will be A. Okay? That area will be A. So this area will be A. So this whole area, so this area over there, that area will be A. Even this area over here also, that area will be A. So that area will be A. Understood? So that means integration of that ds, okay, integration of this ds will be equal to how much? Integration of this ds will be equal to A. That means the area of those n caps, okay? The area of those n caps. So from here it means that this will be equal to E, then this will be equal to A plus E into A. That means E into A and E to A, that will give you 1 twice EA. And further, this pi from electrostatics, from Gauss law, we know that pi is equal to 1 Q divided by epsilon naught. This is from 1. This is from Gauss law. This is from Gauss law. So from Gauss law, this total flux can be replaced by Q divided by what? Q divided by epsilon naught. Q divided by epsilon naught. So from here, we can find the electric field, but also we have determined that Q is equal to sigma into A, okay, previously. So from here substituting, that means Q can be substituted by sigma and A. Q can be substituted by that sigma and A, and we have this epsilon naught. This will be equal to twice EA. From here, some of the terms will get neutralized, like this A and this A will get cancelled. So you get E. Okay? E will be equal to 1. E will be equal to sigma divided by 2 epsilon naught. This is the formula or the important final result for the electric field due to a charged plane sheet. Okay? If we have a plane sheet in this form, and only one side, okay, one side is charged, then the electric field E will be equal to sigma divided by epsilon naught. This is true only for sheet charge only on one side. Okay? Sheet charge only on one side. So from here, when the sheet has charges only on one side, very important, then the electric field E is given by sigma divided by epsilon naught. This is a very important formula that we have to remember. Okay? This is a very important formula we need to remember. Only for the case when the charges has only the charge on one side of the sheet is only on one side. Then we will consider some of the special cases from here. So some of the special cases will be if we consider two sheets. Okay? If we consider two sheets, say like for instance, this is the sheet number 1, okay? And say like for instance, this is the first sheet, this is the second sheet. Okay? This is the first sheet, and that is the second sheet. Sheet number 1, sheet number 2. Then from here we will put an assumption that let the more number of charge density are on the sheet 1 and less number of charge density are on sheet 2, and also that both these sheets are having the same charges or like charges. Over here, if I say like charges, that means on first sheet positive charge, on second sheet positive charge. But using this condition, more charge density on the first sheet and less number of charge density on the second sheet, which means if sigma 1 and sigma 2 are the charge density, if sigma 1 and sigma 2 are the charge density corresponding to first sheet and second sheet, then sigma 1 is more than sigma 2. Now if we look closely with respect to this first sheet, if I consider only on one side of the sheet the electric field due to this side, that means this electric field will be on this direction, and from the other side the electric field will be on this direction. And this electric field, due to the charge, due to this first charge, will be pointing on the other direction. So this, all these will be 1. All these will be electric field E1, E1 of 1 of the first charge, okay, of the first sheet, I mean, okay, of the first sheet. So representing in that way, representing in that way, representing in that way, representing in that way, we can find, we can represent all those electric field vectors. Say, like for instance, over here, if I take this vector across this part, that means it is pointing on this direction. Due to the other side, the electric field vector will be pointing on that direction, okay, due to this n, and due to the opposite side, the electric field will be pointing radially outwards. And from here also, due to this, okay, due to one end of due to one end of the shield, this will be electric field E1. Okay, this will be electric field E1. So this is your, this E1. Due to the opposite phase, that means the electric field will be moving in this direction, okay, in that direction. Due to this phase, electric field will be pointing on that direction. So this electric field also will be E1. That means it will go through the second sheet. This electric field E1 of the first plane, this electric field E1 of the first plane, it will move through the second plane. So we will take another vector and let this vector be pointing on this direction. That means I will represent in that way. Okay? So this also will be 1. This also will be electric field E1. Okay? Now with respect to this second sheet, with respect to the second sheet, if you look from this opposite phase, that means if I draw electric field lines, that means electric field lines will be on this direction with respect to this sheet, okay, with respect to that sheet. So this will be equal to E2, and another electric electric lines of force, it will be also in 1. It will also be on this direction. Okay, it will also be on that direction. So that is also E2, and this E2 will move on this direction. So we'll have to represent these in terms of what? In terms of vectors. Okay, you have to represent them in terms of vectors. So we will take these vectors from below to represent those electric field lines. Okay, electric field lines. Okay, with respect to that, that will be E2, and another, this will be on this direction, and this will be electric field E2. Okay, this also will be electric field E2, pointing on that direction, and because of this we have another electric field vector which points on that direction. So this is also 1. This is also electric field E2. So when you look over here, okay, when you look in this diagram, that means I can consider this as region 1. I can consider this region between the two plates as region 2, and I can consider this region outside behind this second sheet as region 1, as region 3, as region 3, region 1, region 2, and region 3. In region 1, the electric field lines E1 and E2 are in the same direction. So if these are in the same direction, there will be net electric field. Now if you look on region 2, the electric field lines E1 and E2 are acting in opposite direction. See, they are acting in opposite direction. Whereas in region 3, they are acting in the same direction. So for region 1, this will be E1. That means since they are acting in the same direction, so that is why we take the positive sign. Why? Because they are acting in the same direction. Then from here, from the formula, it is sigma divided by 2 epsilon naught plus, okay, sigma divided by 2 epsilon naught. So when you work out the math, that means you will get sigma divided by epsilon naught. This is your electric field in your first region. In the second region, that means from here, since E1 has more number of charges, you can take that to be what? You can take that to be positive. This is E1, and since this E2 is in opposite direction, so we'll take as what? We will take as negative. Why E1 is more than E2? Because charge density on 1 is more than charge density on 2. So from here, the electric field, will be given by that equation. Okay? It will be given by that. It will not be equal to 0. Okay? It will not be equal to 0, but you have to write, okay, sigma divided by 2 epsilon naught, sigma 1 minus sigma 2 divided by 2 epsilon naught. Sigma 1 divided by 2 sigma 2. Even over here also I can write sigma 1 divided by 2 epsilon naught, sigma 2 divided by 2 epsilon naught. Provide this, okay, this relation is true. This relation is true only if we have, if sigma 1 is equal to sigma 2. Okay? Otherwise, this relation will follows. Okay? That relation will follows. So in this case also, in that case also, the electric field, since they are acting in the same direction, E1 also in the same direction, E2 also in the same direction, so the total electric field on the region number 3 will be addition of E1 and E2. So from here you will have what? You have sigma 1 divided by 2 epsilon naught plus sigma 2 divided by 2 epsilon naught. Okay? So these are your one. These are our formula. These are our formula. On region 1, on region 2, and this will be on region 3. Then when the charges on both sheets are unequal and opposite, okay? Unequal and opposite. On, this is the first sheet and this is the second sheet. We find out that there are more number of charge density on the first sheet than on the second sheet. Even if you look on here, more number of plus charges, less number of minus charges. So charge density on 1 is more than charge density on 2. But over here, the difference is that on the first sheet we have positive, and on the second sheet we have what? The negative charges. Okay, the negative charges. So from here, with respect to this one, the electric field lines will be represented. The electric field lines will be represented by this vector, and along the other side also the electric field line will be represented by that vector. Okay? And due to this vector, the electric field line also will move through this electric field, will pass through the second sheet. Okay? It will pass through the second sheet. So this is your E1 vector. This is also our one E1 vector. Okay? E1, and this is also E1. Then with respect to the second sheet, since for negative charges, all the fields will be directed inwards. Even if you consider for this sheet, all the electric field will be directed radially inwards. So that is E2, and this is also E2. So we will take these vectors, we will represent these vectors, and these vectors will represent this direction of what? This direction of E2. Why? It is pointing inwards because sheet 2 has what? Has negative charges. So that will be what? That will be electric field E2. Even from here also, with respect to this side of the sheet, that means the electric field lines will be directed radially inward. So that will give us one. That will give us our electric field E2, pointing on this direction. Pointing on this direction. Okay. So when you look on that region 2, the electric field lines are acting on one. The electric field lines in this region 2, they are acting in the same direction. Due to this E2, which is acting on this direction, on region 1, because it is moving on this direction, that means this also will be moving on that direction. Okay? That will be moving on that direction as well. So this will be electric field E2. Okay? So on E1, both the electric fields are acting in opposite direction. Okay? So which means that this equal to minus E1 on this direction and E2 on this direction. So it is minus. So we have sigma 1 divided by 2 epsilon 1 minus sigma 2 divided by 2 epsilon 1. This is your total E. Then for region number 2, okay, for this region number 2, both these are acting on the same direction. So E1 and E2 is positive. E1 and E2 is positive. So again, the equation like this: 2 by sigma 1 plus sigma 2 divided by 2 epsilon 0. So this is the total electric field. And in region 3, E1, E2 and E1, E2 and E1 are oppositely directed. So the total electric field will be what? Will be negative E1 minus E2. So over here you have sigma 1 divided by 2 epsilon 1 minus sigma 2 divided by 2 epsilon 1. So this is your electric field. And from here we can represent the total electric field by this vector. This green vector will represent what? Will represent our total electric field E. Okay, total electric field E, which is what? Which is the addition of E1 and E2. So from here, these are what? These are some of the peculiar results that we need to learn about electric field due to two parallel plane sheets. Okay? Due to two parallel plane sheets. Likewise, we can also represent over here there will be no electric field. Why? Because they are oppositely directed. The total field will be purely on this direction. The total electric field will be purely on this direction. Okay? One electric field on this side. This will be one electric field on this side because due to the addition of this and this, and another electric field, okay, another electric field will be on this direction. This is your E. So due to what? Due to the addition of this and this. Okay. Then for the third case, okay, when both the charges on both sides are equal and opposite. Okay, when both the charges are equal and opposite, which means that over here you have these charges which are positive, okay, positive. All these charges on these sheets are what? Are positive, but they should be equal number of charge density. Okay, equal number of charge density. So we write like that. That means on both sides of the sheet we'll be having positive charge, and from here we have the negative charges. So over here we have the negative charges, and then we will represent them in terms of electric field lines. Due to this first sheet, this will be one vector. Due to this sheet also, another electric field lines will be represented in that form. And due to this vector also it will be on this side. So from here, the electric field line due to the first sheet will be pointing radially outwards. Due to the other side also the electric field lines will be pointing in this direction, and due to this E1 acting on this direction, we have another vector which acts on this direction. This is also what? This is also E1. But mind you that the charge density on both sheets are what? On both sheets are equal. Then next, with respect to the second sheet, this is the second sheet and this is the first sheet. With respect to the second sheet, we know that since there are negative charges, all the field lines will be directed radially inwards. So we'll take this vector and this will be the vector acting on that direction. So this will be what? This will be E2 due to the second sheet, acting radially inwards. Even for the second sheet also, due to this phase, that means the electric field line, okay, this electric field line will act on that direction. So from here, that means this will be what? This will be electric field line E2. And due to this electric field line with pointing inwards towards 2 and pointing inwards towards 2. Even from here also, with respect to this vector, that means on region 1, we have another vector which acts on 1, which acts on this direction. This also will be electric field lines E2. But when you look closely on region 1, E1 is acting on this direction and E2 is acting on this direction, opposite. So there will be no net electric field. Okay, even from here also, the electric field lines on E1 and the electric field lines on E2 are opposite, so there will be no electric field. So the net electric field will be only on this second region, okay, only on region 2 there will be electric field. So we will represent this by its third vector. Why? Because this net electric field, capital E, will be acting on this direction. It is due to the addition of E1 and E2. So this will be E1 and E2. So this system of arrangement, we will learn that it is very applicable for the case of one device which we will learn in this chapter, which is dealt as well as a capacitor. It is that type of device which will store charge. Okay? So from here, let us work out the electric field inside. So the electric field inside will be E1 plus E2. Why E1 and E2? Because E1 acting in the same direction, E2 also acting in the same direction. So from here, this will be sigma divided by 2 epsilon naught. Even from here also, this sigma divided by 2 epsilon naught. So when we work out, we get the formula. That means the electric field inside 2 parallel plate capacitor is given by 1. It's given by this expression. So from here, you can do by yourself that since these are negative, so it will be equal to 0. Even from here also, since this E1 and E2 are negative, so it will be equal to 0. So the rest of the discussion you can work out by yourself to understand the details. Thank you.